I'd like your feedback on this black background. If you think it's easier to see this way, please let me know. On the last video, we defined what a subgroup of G is. It is a subset, a non-empty subset of G that is a group by itself using the operation of G. And we saw that we really just need to show two things. One, we need to show that H is closed under the operation in G, and we need to show that inverses exist. Once we have inverses, we have H inverse equals E, and of course we inherit, H inherits associativity from G. Note the additive notation. We say show H inverse is in H, but what we mean by H inverse in the additive case is show that minus H is in H. So we move on now to a one-step subgroup test. Let AB be in H and show that AB inverse is in H. That is sufficient to show that H is a subgroup of G. Again, notice the additive notation. If we're showing AB inverse is in H and addition is the operation, then what we are doing is showing that A minus B is in H. We have to prove that this one step is enough, so I will prove it by showing that steps 1 and 2 in the two-step test are satisfied if we just know that AB inverse is in H for all AB in H. Well, first of all, we know that H is non-empty, so we can say let A be an element of H. Now, using A as the two elements, I can say then A inverse is in H, and of course that is E. E is in H. So having E in H, now I will use E and A to show that A inverse is in H. So I will say E, A inverse, is in H, which of course means A inverse is in H. So we've satisfied step 2, and now for step 1, to show that H is closed, I have to pick two arbitrary elements in H, let AB be in H. Then, by what we just proved, we know that B inverse is in H. So, A, B inverse is in H, and that is equal to AB. So we have shown that it is closed, H is closed, and that inverses exist. Therefore, this is enough. So that is a one-step test, and actually there's something even easier if G is a finite group. If G is a finite group and H is a non-empty subset of G, all you have to do is show that H is closed under the operation of G, if G is finite. Now, why is this sufficient? Well, let's go back to the two-step test. We know that H is closed under the operation of G, so really all we need to do is show that inverses exist. So I want to let A be an element of H, remembering now G is finite. Let A be an element of H, and I want to find its inverse in H. Well, if A is in H, consider this set, A squared, A cubed, ... all powers of A. This is clearly a subset of H because H is closed under the operation. And we know that G is finite, so of course H is finite. And let me write, since this set is finite, because G is, we know that A to the K is equal to a to the j for some k greater than j. So this would tell us that a to the k minus j is a to some positive power that is equal to the identity. K minus j is greater than 0. So I could write this as a times a to the k minus j minus 1 is equal to e. By uniqueness of inverses, then, this, since it's multiplied to a gives us e, tells us that A inverse is a to the k minus j minus 1. So inverses exist. And we have shown that all you need to do, if you know that G is a finite group, is to show that the set H is closed under the operation of G. In that case, H is a subgroup. Say, therefore, H is a subgroup of G. Our first example is a set H, a subset of the general linear group, all matrices with determinant a power of 2. We want to prove that H is a subgroup of the general linear group. Now to do that, I'm going to have to verify that H is non-empty, and then all I have to do is prove that AB inverse, I want to show that if A and B are in there, that AB inverse satisfy this membership rule. In other words, my plan is to let A and B be in H and show that AB inverse is in H. To show it is in H, I have to show that the determinant, the membership rule, applies to AB inverse. The determinant of AB inverse has to be a power of 2. So that's my plan. Well, I need to first verify that H is non-empty. H is clearly not the empty set because, I use BC for because the determinant of the identity matrix is equal to 1, which is a power of 2. So the identity matrix lives in H. It satisfies the membership rule. Therefore, I can say let A and B be matrices in H. I want to show that AB inverse is in H. So, according to plan up here, I want to show that the determinant of AB inverse is a power of 2. Well, A and B are in H, so we know that the determinant of A is 2 to the k for some integer k, and I know that the determinant of B is a power of 2, so I'll say 2 to the j for some integer j. Now I want to figure out the determinant of AB inverse. So I'll just start the determinant of AB inverse. I want that to be a power of 2. Well, that's equal to, we know that it's the determinant of the product is the product of the determinants. So this will be the determinant of A times the determinant of B inverse. And we know that the determinant of B inverse is 1 over the determinant of B. So this is determinant of A times 1 over the determinant of B. And we know that the determinant of A was 2 to the k, and 1 over the determinant of B will be 2 to the minus j. So we do have a power of 2, 2 to the k minus j. Since k and j were integers, we know that k minus j is also an integer. Therefore, we have proven that H is a subgroup of G by using the one-step test. I wanted to do an example where we are using additive notation. So take the group G, the set of all 2 by 2 matrices with integral entries. That is a group under matrix addition. And H is a subset of G, and it is the set of matrices with integral coefficients entries where the entries add up to 0. We want to prove that H is a subgroup of G. So our plan is as follows. We have to verify that the subset is not empty, and then we have to let A and B be in H and prove that A minus B is in H. Remember, A minus B is instead of AB inverse because we're using additive notation. Okay, so let's do that. Well, clearly 0, 0, 0, 0, the identity for G is an element of H. So H is not the empty set. That gives us permission to say, let A, and I think I'll say A equals, let's do A1, B1, C1, D1, and B equals A2, B2, C2, D2, B in H. Let them be in H. Well, then, before I start worrying about how I'm going to show A minus B, I want to write down what that means. Then A1 plus B1 plus C1 plus D1 equals A2 plus B2 plus C2 plus D2, and that is 0. They satisfy the membership rule for H, and that membership rule is this. Now we want to show that A minus B satisfies that membership rule. Well, that's very easy. A minus B is equal to the matrix with entries A1 minus A2, B1 minus B2, etc. And all we have to do is now add up those entries. Adding up the entries, we can associate them like this, and we have A1 plus B1 plus C1 plus D1 is 0, minus, and we know that the second sum is 0, so we have shown that A minus B satisfies the membership rule of H. So this implies that A minus B is an element of H, and therefore by the one-step rule, we have proven that H is a subgroup of G. I think I've run out of room. I'll do it right here. Therefore, H is a subgroup of G. Now I want to give you a definition of a subgroup that is used often in this course. The centralizer of an element A in G. So A is a fixed element. It's not arbitrary. Pick an element A in G and define its centralizer. Its centralizer is given here. The centralizer of A is the set of X in G that commute with A. Note, if G is abelian, what is the centralizer of any element? It's the whole set, isn't it? The whole G, it's all of G. So if G is an abelian group, this is not an interesting subgroup. It is, in fact, the entire group itself. So we'll be looking at examples of centralizers in non-abelian groups. Let's look at these first two little examples just so that you see what the centralizer is. And by the way, when I give an exam, I always ask questions this way. I'll define a subgroup maybe that you haven't seen before, and I'll ask you to to find examples of that subgroup in given, like in 1 and 2 here. And then I'll ask you to prove something about the subgroup in general. So we're going to find the centralizer of R and the centralizer of H in D4. Well, the centralizer of R is simply the elements in D4 that commute with R. So we know that certainly R commutes with any power of itself. So we have R squared, and R cubed in the centralizer. And you might try to see if it commutes with any of the flips or the reflections, but you will find it does not. So the centralizer of R is simply this 4-element subgroup. The centralizer of H, those elements of D are that commute with H. Well, we know that E commutes with everybody, and certainly an element commutes with itself, so we have E and H in there. We also know that HR squared equals R squared H in D4, so H commutes with R squared, not with R. So there is one other one it commutes with, and you would have to just try some to see, but HR squared also commutes with H. So we have another 4-element subset, the centralizer of H. Now for the next example, we want to find the centralizer of a matrix in an infinite group, GL2R. So the only way I can think of to do this is to assume that a matrix A, B, C, D is in the centralizer of the matrix 1, 0, 0, 2, and just solve for what must be true about the entries of that matrix. So I wrote out the two products, and we get, if we multiply by A, B, C, D on the right, we get this product, and on the left we get this one, and these we want to be the same. Well, looks like we could use any A and any D, but for B to be equal to 2B, B has to be 0, and for 2C to be equal to C, C has to be 0. So this tells us that the centralizer of the matrix 1, 0, 0, 2 is equal to the set of all matrices of the form A, 0, 0, D, where A and D are integers. This would be the centralizer. So now we want to prove in general that if G is a group and A is an element of G, that the centralizer of A is a subgroup of G. So the first thing we have to do is show that it is non-empty. Well, the centralizer of A is certainly not empty for any A, because E commutes with A. So E is always in the centralizer. So it's not empty. And now we want to use the one-step method. Let X and Y be in the centralizer of A. And I know that I want to show that XY inverse is in A. So I'm going to go over here in yellow and just kind of pretend that's on scratch paper. I know that I need to show that XY inverse is in the centralizer, so I need to show that XY inverse A is equal to A XY inverse. All right, well, let's see. What if I just started out with that right-hand side? I see right away that I need to show that Y inverse commutes with A, or I'm not going to be able to go anywhere. So the first thing I'm going to do is show that Y inverse commutes with A. So we'll begin the proof by saying, well, I know that if x and y are in there, I know I want to get y inverse. Well, first I'll just write xa equals ax and ya equals ay, because x and y are in the centralizer. Okay, but I'm going to take this one. I want to get y inverse in there, and I'll just multiply on both sides and get y easily. Let's multiply on the left by y inverse. So I have y inverse ya equals y inverse ay. These cancel, that's e. So I have a is equal to y inverse ay. And now I'm going to multiply on the right by y inverse, and I get exactly what I want. A y inverse is equal to y inverse a y inverse. I multiplied on the right. These two cancel, and I have then, this gives me what I need. A y inverse is equal to y inverse a. Now I can go up and show that xy inverse commutes with a. All right, so now let's take a times xy inverse. A commutes with x, so that is xa, y inverse. Y inverse commutes with a, and so we have x, y inverse a. So we can conclude then that xy inverse is in the centralizer of A, and hence the centralizer of A is a subgroup of